Hi, welcome back to class Advanced Artificial Intelligence. This is a practical part, and the practical part is divided into three subparts, part two, part three, and part four. They're all in explaining one example, but in three different parts because of the length of the example. It's a simple example. We try to implement it with using LSTM. So LSTM, a good way to explain LSTM and to remember it is that we have four gate, and the purpose of this gate is to erase old memory or to ignore old memory. And input gate is to write new memory, and output gate is to read memory. So here we have a practical example of input synthesis. I like Rojava. So I'm going to do in this part, practical two, only the word I. I will enter it to the LSTM and we get the output. And the next video will be like, and the after will be Rojava. So these are three words, and we're trying to work with these three words and put them into LSTM and see how LSTM will process these words sequentially. Now, step one, we try to define or declare our vocabulary, word encoding, vector dimensions, and LSTM hidden size. So for the vocabulary, from the sentence I like Rojava. So I is one, index one, and like is two, Rojava is three, and vector size is three. One hot encoding, each word becomes a vector of size three. For example, I is here, so that's one, zero for like, zero for Java. Whereas like, it is one, zero for I, and zero for Java because the focus is like. So that's one. That's why it gets one. Rojava is zero for I, zero for like, and one is for Java. That's a good way of telling the computer to encode and to understand it. Now, dimension, we have three inputs, I like Rojava. So three inputs, and we have two inputs for the hidden state. Now, sequence, we have, because we enter this input in a sequential manner. So I at time one and at time two like at time three Rojava. Now, initial state, we have hidden zeros, nothing there, initial state. We have cell state, nothing, zero. But we have input vectors. I like Rojava, so that is x1, I100, and 010, and 001, that's for Rojava. Now, here is the diagram for LSTM, that's for gate, and this input gate, and this is candidate memory, and tangent input of the tangent of the input. And here is the output gate, and that's also memory at previous state. Now, um, so set up the parameters at every time step. We have for gate, and we have so the information to be removed from memory and decide what information to enter memory. That's input gate. Candidate memory, create new candidate content, and the output gate controls what part of memory becomes output. Now, concatenation, what we'll do, we will concatenate hidden with the input. So hidden states, which are only two neurons, and input vector, which are only three digits. Okay, three digits, 100, 010, and 001 for three words. So there are three digits. So here, example for time one, for I, hidden is 0, uh, X1 is 100. So concatenate this and this, you will get that one. Now, we will initialize weight matrix because we have five weight matrix for gate weight matrix, input weight matrix, candidate memory weight matrix, and output weight matrix. All of them five because we have three inputs plus the hiddens, that's five. So concatenate, and then there are two neurons in the hidden. So 5 by 2, 5 by 2, 5 by 2, 5 by 2, all of them. Now, biases to, in each layer or each network, for example, for gate bias, and we have input bias, we have candidate bias, we have output bias, and dimension is two neurons for bias. Now, here we initialize forget gate weight matrix. That's the weight matrix, and this is the bias for it. Now, this is the input gate weight matrix, and this is the candidate memory weight matrix with its bias for input gate. And the output gate, again, 5 by 2, 5 weight matrix by 2. And this is two biases. Now for gate for calculation, if we have input and H00, concatenating them, that is the input will be to the network. So 5 by 1, that's the input. 00 is the hidden T minus 1. We have 0 at T minus 1 hidden 00, and then that is the input layer 100. Now, we do the forget gate here. So this HT minus 1, 00 with XT 100. So they get concatenated and will be multiplied by the weight matrix and then subject to sigmoid, and we get the output of the forget gate. So let's do it. Here is the forget gate. That is the sigmoid weight matrix for forget gate, hidden at T minus 1 and XT at T, current XT, plus bias for forget gate. So this weight matrix, and that's the bias. So here, that's the input and that's the weight matrix. We multiply them. Okay, so 0.7 multiplied by 0, 0.2 multiplied by 0, 0.5 multiplied by 1, and so on and so forth. 0.7 multiplied by 0, 0.2 multiplied by 0. And for the second row, 0.4 multiplied by 0, 0.6 multiplied by 0, 0.2 multiplied by 1, you can see, and so on and so forth. That's the result for the calculation, 0.5 and 0.2, plus the bias, which we assume them as zero point 0.1 and 0.1, so 0.6 and 0.3. Subject them to a sigmoid function. We subject them to sigmoid function, we will receive this and this. So that is the output for the forget gate. Forget gate. So that's the output for the forget gate. So this is the output here. The output here, we found it. Okay, two values. Now, since we have still C dot, previous candidate memory is 0, so this will matter later when updating the cell state. Now, let's come to this one now. We are doing this one now, input gate. So here, the input gate, again, that's the formula for the input. Only difference is the weight matrix here, I think, and the bias related to the weight matrix. So here, same input, which is concatenate of the previous hidden plus the input, multiplied by the weight matrix plus the bias. So here is the zero point 0.6 multiplied by 0, 0.4 multiplied by 0, zero point 0.3 multiplied by 1. And you can see for the second, uh, zero point 0.5 multiplied by 0, zero point 0.1 multiplied by 0, 0.6 multiplied by 1, zero point 0.3 multiplied by 0. So, and you can see the result is this one. Now that's also done. Uh, we add them to the bias that we have. Again, we assume zero point 0.1 by zero point 0.1. So subject them to sigmoid. Again, here this value, subject this zero point 0.4 to sigmoid, zero point 0.7 to sigmoid, and we receive this one and that one. So what means, just let you know that here, 64% means that they will be kept, and the rest will be thrown away. 75 for the second neuron will be kept, and the rest will be thrown away. Here, it means what? Here, for the input means 60%, nearly 60% and 67% of the new candidate memory to enter the cell. So they will be able to enter the cell. So that is the result of this one here found. Next, we are going to apply this here. We will do candidate memory here. Okay, so formula is C tilde tangent H WC concatenate input with the hidden plus B, and the sigmoid will give you an output range between -1 and 1. Now, again, this is the concatenated input, that is weight matrix for the candidate memory. And here we multiply it, and we will get the result with the tangent. And so the result will be this one. The result would be this one here. So final candidate memory, it will be this one. Now, it means that final candidate memory, we found this one. Okay, that's done. That's tangent, okay? This one, that's done. Tangent edge. Okay, so that's done. Now, this is new potential information extracts from the word I. That's all we have doing, only I. So the I like Rojava, that's only I. So, and at T1, we have forget layer, forget gate, output and input, and the candidate memory. Now, next we are going to do this part, okay, which is forget multiply by initial candidate plus input layer, input multiply by candidate memory that we found. So in other words, this and this we will get, and then I multiply by C1, it is I multiply by C1. So we will get this one, this part, okay? And then we plus them with this one. We plus them with this one. So this, they will be, so this one and this one, they will be plussed. So we get this information here. Now let's do it. Forget multiply by C dot. This is, I think, is 0. So you'll have nothing. So forget is this one, and I is this one, and C dot is 0, and C dash tilde, we found it, which is candidate memory, but initial memory is 0. So this whole part is 0, nothing. So in other words, this whole part is 0, nothing, because this is whole part is 0. And then, so now remaining this part, this multiplied by this, and then plus the zero, which will be only that one. So I multiply by C tilde, I multiply by C tilde, I multiply by C tilde. That's the input. Multiply by C tilde, which we have it. Um, so so that's zero, and this one I multiply by C tilde. So this I input, and that's C tilde. So this is the information that we received. Okay, so that's the information that we received, plus the zero that we have it nothing because from the forget multiply by initial memory. So that is the result that we receive. CU1 is 0.321, 0.132. So in other words, it is this here, that result. It's here. So C. Now, next we try to find the output. Next, we try to find the output. So if I go back here, output can be found by sigmoid, weight matrix for the output, the concatenate hidden with the input plus the bias of the output. Again, that output from here, which will be plugged into this equation, multiplied by tangent C1 that we found it, tangent C1, this one here that we found it, then we get the output, complete output. So it's simple. Let's do it. We are still in time. Step one for I. I like Rojava, just word I, just word I. So for the output, similar, that's the concatenated input multiplied by weight matrix plus the bias. So concatenated weight matrix multiplied by concatenated input plus hidden um, multiplied by weight matrix. So zero point 0.3 multiplied by 0.7 multiplied by 0.5 multiplied and so on and so forth. For the second of zero point 0.8 multiplied by 0.1 multiplied by 0.4 multiplied by 1. Zero point 0.4 multiplied by 1. So it is found that is the result of multiplying input by weight matrix plus the bias, which we assume for all layers, for all networks, zero point 0.1 by zero point 0.1. So they will go under sigmoid, and it was found output. Now plug it into equation, last equation, which is H1 out multiply by tangent C. C is this, just take you, that's the C that we found it. And here we found the output. Output multiplied by this. So this, and then we get H1. So very simple if we are doing it. So output, that's output multiplied by C. That's this dot means that element wise. So element wise. So 0.645 multiplied by 0.310 and 0.622 multiplied by 0.131. So element wise. So that is the H1. H1 will be important for the next input, which is like the word like. So that is the first part of the practical part. We have a time one, like I. We entered to the network. We found the forget gate for it, the results. We found the input I. We found candidate memory. We found CL, C1, and output and hidden. So stay tuned for the second word, which is like. We have I like Rojava. So we did so far only I. Thank you.